Okay. So we'll start talking about autoregressive moving average models today. Last presentation, ST06 ARMA models. Okay. We already saw the autoregressive models, and talked about the moving average models. Now, the ARMA models are just a generalization of both and joining both types of models together, essentially. So we call the ARMA PQ process. We will use P for the order of the autoregressive polynomial. We'll use Q for the order of the moving average polynomial. And we'll keep working with this Z tilde, which is already a centered version of the original series. Okay, so already subtracted the mean. Now, the ARMA model can be written in this form. I have an autoregressive polynomial applied to ZT, and that is equal to the moving average polynomial applied to AT, where AT is, as it's been so far, white noise. Okay. So in other words, our model is 1 minus phi 1b minus phi 2b squared minus phi 3. Pardon me?
Voy a ver Arma y Arima.
Let me mute everybody. Everybody appears muted already. Okay. So essentially, we're saying that the ARP polynomial is a polynomial of order P, backshift polynomial. So we have minus phi 1b minus phi 2b squared minus up to minus 5p b to the p. And that applied to ZT is equal to 1 minus theta 1 b minus theta 2 minus up to theta q b to the q. That is ZT, if you put all these terms from here to the other side of the equation, what it says is that ZT is dependent on ZT minus 1, CT minus 2, ZT minus 3, up to CT minus P, and also dependent on AT, AT minus 1, AT minus 2, up to AT minus Q. Okay, so the common notation is this is the standard notation for an ARMA PQ model. P order of the autoregressive polynomial, Q is the order of the moving average polynomial. Okay, now these models arise for different reasons, but actually most of the models we'll find in practice are not going to be purely AR or purely MA. Okay, so all of these models that we'll be dealing with will have both components, autoregressive and moving average components. Now, there are some typical cases where these type of models arise. For example, when we aggregate components, such as is the case of the gross domestic product, okay, because that's the aggregation of series from different economic sectors, or series that contain observational errors, which is almost all series. I mean, there's always a random error that fluctuates around, but this in particular refers to series that arise with observational errors. For example, in a manufacturing process where we are measuring the diameter of some pistons that are coming out of the manufacturing process, and those measurements are subject to errors. So those cases normally gave rise to the autoregressive moving average models also. Now, if a series satisfies this relationship, that is when the series is the sum of two series, W1T and W2T, where W1T and W2T are two independent processes with mean zero, then what happens with the behavior of this series is going to depend on what is the behavior of W1T and W2T. So this is another form that these ARMA processes arise. For example, if W1T is an ARP model and W2T is white noise, then we have an ARMA PP. That is the moving average component is of order P. Okay. So adding an ARP with white noise gives us an ARMA PP. If we had an ARP1 and an AR2, a P2 process, then the sum of two autoregressive processes of order P1 and P2 will be an autoregressive process of order P1 plus P2 and the maximum of P1 and P2. Okay. That will be an ARMA with P equal to P1 plus P2 and Q equal to the maximum of P1 and P2. If we have two processes, an ARMA P and an ARMA Q, then the result will be an ARMA P plus Q. So we have the sum of P plus Q will be the order of the moving average polynomial. If, on the other hand, we have a moving average of order Q and white noise, then the process will be a moving average process. Okay. If we have moving average and we have noise, we get a moving average process. An ARMA 0, that is, we don't have the order of the autoregressive polynomial is 0, and Q terms for the moving average process. Okay, so you can see the difference here. If I add white noise to an ARP, I get an ARMA. If I add noise to an MAQ, I get an MA process, okay, which is an ARMA and 0Q. If we have two MA processes with orders Q1 and Q2, then we get again a moving average process with orders maximum Q of between Q1 and Q2. So the sum of two moving average processes give us another moving average process of order maximum of the Q1, which is the order of the first moving average process, and Q2, which is the order of the second one. And we have an ARMA PQ, and we add white noise, we get an ARMA P, and the order, what changes is the order of the moving average component, which becomes the maximum between P and Q. Okay. So those are particular cases where we have we're adding two processes that have either autoregressive or moving average parts, or in this case, which is an ARMA already, and we add white noise. Okay. So these are different forms that we can get these type of models, these ARMA models. The easiest case is when we have a moving average process and we have white noise, or when we have two moving average processes, because what we get is a moving average process. Okay. Now, of course, we will not dig into the proof of any of these statements, but if you look at them, and it sort of makes sense given the properties of the autoregressive and the moving average processes. Now, let's start with the simplest case. Just as we did when we studied the autoregressive models, we started with an AR1. With the MA models, we started with an MA1. Now, let's start reviewing the characteristics of an ARMA 1-1, which is the simplest case of an autoregressive moving average model. Now, the conditions for invertibility and stationarity are the same. I mean, for the process to be stationary, phi has to be less than 1 in absolute value. That is, the root of the polynomial y minus phi x equal to 0. That root has to be outside the unit circle. That means that it has to be greater than 0, so greater than 1. So in absolute value, so phi would have to be less than 1 in absolute value. And for the process to be invertible, we have the similar condition on theta, that theta in absolute value is less than 1. Okay. So in the ARMA processes will still be requiring that the processes are stationary and invertible. Okay, so stationarity imposes conditions on the AR coefficients, and invertibility imposes conditions on the MA coefficients. Okay, so we need invertibility and we need stationarity. If the process is stationary and invertible, then we can write it either as an AR process, because we saw already that if a process is stationary, it has a representation as an autoregressive process. Okay, if the process stays in stationary and invertible, then we can write down, since it's stationary, I can write ZT as 1 minus theta B. Let me put it here. Like, if it's stationary, we know that I can write this thing as 1 minus theta B times 1 minus 5B inverse applied to AT. Okay, so because if it's stationary, then this polynomial here, the inverse of this polynomial, is an infinite sum of white noise, but that infinite sum of white noise will have the property that the sum of the psi weights will converge. And if the process is invertible, so if this is stationary, and we can do this thing because of the process is invertible. I'm sorry. Okay, if it's invertible, I can express AT, white noise, as a linear combination of the previous values of ZT. If it's stationary, I can write ZT as a linear combination of current and previous values of AT, which is what these expressions say. Because if it's stationary, I can compute this thing, and the mean and the variance will converge. And if it's invertible, I can compute this thing also. Okay, because theta will be less than 1 in absolute value. So because of the stationarity and invertibility, that sum of the absolute values of the psi weights and the pi weights converge. Okay, so far, are we okay so far? Okay. This is just what we have seen already. When I have a process that is stationary, then 1 minus 5B inverse, this thing here, is 1 minus 5B inverse. Then I have that ZT is 1 minus theta minus phi B minus phi times theta minus phi and pi squared and so on. Okay, I just keep multiplying this 1 minus theta times all these terms in this polynomial. So if the process is stationary, then phi is less than 1 in absolute value, and in this case psi sub j, the coefficients of this representation of the model, the psi weights, are phi to the I minus 1 times theta minus phi. Okay, so that will be the psi weights for the representation of ZT as psi of B AT. So this will be the coefficients of AT. You can see it here. When I is equal to 1, I have phi to the 0, which is 1, and I have theta minus phi, which is this term here. Then the next term is phi is equal to 1 times theta minus phi, and then the next one is phi squared theta minus phi. Okay. So those are the psi weights. Now, On the other hand, if the process is invertible, then I can write a t as 1 minus 5b over 1 minus theta b, where this is 1 minus theta b inverse. And that's when I do the multiplication, I get something similar to what we got with the when we had the psi weight representation. Now this will be the pi weights, okay? So remember, this will be writing this thing as pi of b applied to ZT, okay? So in this case, all the pi weights for the for this polynomial pi of b are theta to the j minus 1 phi minus theta, okay? So when j is equal to 1 is 1 times phi minus theta. When j is equal to 2, I have theta times phi minus theta, and so on. So that's the case for NARMA 1, I have, if it's the stationary and it's invertible, I have both representations as an infinite combination, linear combination of ZTs for the white noise, or an infinite linear combination of the ATs for our series ZT tilde. Now, which are the moments of this process? Well, we can write down CT tilde as phi ZT minus 1 plus AT minus theta AT minus 1. Okay, so all I did is, instead of writing 1 minus phi b ZT equal to 1 minus theta b AT, I just left CT on one side of the equation. Then I have ZT is equal to phi ZT minus 1 plus AT times 1 minus theta AT minus 1. Let's compute the moments. We know that the expected value of Z tilde is 0, because we subtract Z tilde is ZT minus its mean. So its expected value is going to be 0. Now, the variance is going to be the variance of the variance of ZT is going to be expected value of ZT squared, right? Because it has mean 0. So I take this expression and multiply it by itself to get and then get the expected value. So if we do that, then let me see, I think I added a note here. No, it's not here. I'm taking this thing squared. So this is going to be equal to what? When I take this thing squared, 8ZT squared is, let's see, it's going to be the expected value of phi ZT minus 1 plus AT minus theta AT minus 1 squared. And if I square these things, okay, I get ZT times ZT times CT minus 1, okay, times ZT times plus expected value of ZT AT minus theta value expected value of CT AT minus 1. Now, notice that the expected value of ZT AT, this term here, is phi, expected value of ZT minus 1 times AT, plus expected value of AT squared minus theta, expected value of AT minus 1 AT. Now, this term here is sigma squared. And this is 0. Why is this term 0? Why is this term 0? Any guesses? ZT minus 1 What's the expression for CT minus 1? CT minus 1 is equal to phi CT minus 2 plus AT minus 1 minus theta AT minus 2. Now, why is this expected value 0? Expected value CT minus 1 times AT. Any guesses? No?
No.
Because CT minus 1 does not depend on AT. It's independent of AT. CT minus 1 depends only on AT minus 1 and AT minus 2, not on AT. Okay? So since it's independent of AT, the expected value that has the product and the expected value of AT is 0. Okay? And in this case, it's clear that expected value of AT minus 1 times AT is going to be 0 because the ATs are independent. Okay? And they have mean 0. So the only term that I have left is this one, expected value of AT squared. Okay? Now notice that nobody answered, and the answer was here. Okay. Now, if I compute now the expected value, see, I have this, so I took care of this term, right? I took care of this term, and that expected value is just sigma squared. Now, the expected value of ZT, AT minus 1, that's equal to what? Expected value of ZT, AT minus 1 is this one here. And that's equal to phi, expected value of ZT minus 1, AT minus 1 plus expected value of AT minus 1 times AT minus 1 minus theta expected value of AT minus 1 squared. Now, this one here, expected value of ZT minus 1 times AT minus 1 is equal to sigma squared. See, this is equal to sigma squared. That we just developed that here, right? Just instead of using t here, use t minus 1, and that expected value is going to be sigma squared. Because that expected value is sigma squared. So I get phi squared times sigma squared sub A. This expected value is 0 because of the independence of the ATs. And then I have minus theta, and the expected value is t minus 1, AT minus 1 squared. And that is theta sigma squared. So the expected value of CT AT minus 1 is going to be phi minus phi times sigma squared minus theta times sigma squared, or phi minus theta sigma squared. Okay. So what is then gamma 0? Gamma 0, I already know that. Let me erase things here. We already know that this one here, this expected value of CT AT is equal to sigma squared. We already know that this term here is phi minus theta times sigma squared. The only term that I have left is this one here. It's phi times expected value of CT ZT minus 1. And what is the expected value of ZT times ZT minus 1? That's exactly, since CTs have mean 0, this is the covariance between CT and CT minus 1, which is gamma 1. Okay? So I have that the variance then is equal to phi times gamma 1 plus sigma squared minus theta. I just need to reverse the sign here. minus minus theta plus phi, minus theta plus phi times the whole thing sigma squared. Okay, so that's the expression for the variance. So the variance is the covariance multiplied by phi, which is the autoregressive coefficient, plus 1 minus something, the multiplication of these parameters times sigma squared. And this is the autocovariance function. So I can write it down as, we know that for k is equal to the covariance is this one that I have here. Let me copy the equation from here. That's gamma 0. Remember, this is gamma 0. Phi gamma 1. So it depends on the first lag autocovariance times the variance, plus the variance times a constant that depends on the coefficients, on both coefficients, the moving average and the autoregressive coefficient. Now, if we write down what's the covariance at lag 1, the covariance at lag 1 is the expected value of zeta at lag k, expected value of ct minus 1, ct minus k, plus at times zt minus k, minus theta at minus 1, at minus k, right? All I did is write this thing down as the expected, the covariance gamma k, remember the covariance, expected value of zt and zt minus k. And that is the expected value of zt, and zt minus k is equal to zt to phi, zt minus k minus 1 minus plus at minus k minus theta at minus k minus 1. Okay, so you do that multiplication, we get this. This is for the covariance at lag k, and for lag k equals to 1. Notice here, when k is equal to 1, I have ct minus 1 and zt minus 1. When k is equal to 1, okay, so that is equal to the variance, right? When k is equal to 1, let's here the case, k is equal to 1, then this thing here, this is the variance. This is the variance of zt, okay? Because that's when k is equal to 1, is zt minus 1 times zt minus 1. When k is equal to 1, I have at minus zt minus 1. Now, zt minus 1 does not depend on at. So when k is equal to 1, this expected value of at zt minus 1 is going to be equal to 0. And I have minus theta times expected value at minus 1 ct minus 1. The expected value of at minus 1 ct minus 1, as we saw it in the previous slide, is theta times sigma squared. So for k is equal to 1 is phi gamma 0 minus theta gamma sigma squared. If k is greater than 1, what's going to happen here? If k is greater than 1, I have, for example, k equal to 2. Zt minus 1 times zt minus 2. That expected value is going to be what?
The covariance?
That's going to be the covariance one lag apart, right?
Mm-hmm.
It's going to be phi of k minus 1. That will be, if k is equal to 2, that will be the covariance of lag 1, right?
Yes.
And if it's k is equal to 3, that will be the covariance of lag 2. So that's phi times gamma k minus 1. Now, if k is equal to 2, I have at zt minus 2. Or if k is equal to 3, is at zt minus 3. Zt minus 2 does not depend on at. So that's going to disappear. This term disappears. And so does this term, because I have AT minus 1, and I'll have AT CT minus 2, which doesn't depend on AT minus 1. So I only have left this term. Okay. So notice here that the covariance, that what's important to note here is that this covariance at lat k, only for k is equal to 1, involves both parameters, phi and theta. But for k greater than or equal to 2, it only depends on phi, which is the autoregressive coefficient. So the covariance will behave according to the autoregressive difference equation for lags greater than 2, greater than or equal to 2. Okay. So that's these are the expressions for gamma null, the variance, the gamma 1, the covariance at lag 1, and gamma sub k, which is equal to this thing here. Okay.
This is for the simple case, or this is just for general?
This is for the AR. It is for AR11, ARMA 11.
Okay.
Yeah, this is we're still on the simple case of P is equal to 1 and Q is equal to 1. Okay.
Okay.
Okay. Now that's the same slide. Okay. Here's where I added the note, because there have been some questions before. Gamma 0 is, although we did the work in the previous slide, but gamma 0 is phi gamma 1 plus 1. We saw this expression, right? And I can write this thing down as phi times phi gamma 0 minus theta sigma squared plus this in here. And that's phi squared times gamma 0 minus theta phi sigma squared plus sigma squared. All those here are sigma sub a squares, okay? Minus theta phi minus theta sigma squared. So I'm just rewriting this thing in a form so that it falls in this form. I'm rewriting the same equation to express gamma 0 in this form. Okay, because that will be convenient when we compute the correlations. That's the only reason. Okay, because we know what the gamma 0 is. So I express it in this form because I'm gonna divide now, to compute the correlations, the autocorrelations, I'm gonna divide the covariances by the autocorrelations. Okay. Now, since using these expressions here for gamma 0 and gamma 1 and so on, then we can write down the autocorrelation function as phi to the k minus 1 times 1 minus phi theta times phi minus theta divided by this thing. Those are the autocorrelations. And since we're assuming stationarity, phi is less than 1 in absolute value. Therefore, these autocorrelations are decaying exponentially to 0, starting at k equals to 1. Okay, because phi is less than 1. Phi in absolute value is less than 1. Actually, we are assuming invertibility, so that theta is also less than 1. Okay, but important thing is that I have phi here raised to a power for k equal 1, 2, 3, 4. So starting with k equal to 1, when phi to the k minus 1 is going to be 1 here. The next term is going to be rho sub 2 will have phi to the phi squared. Rho sub 3, the third autocorrelation will have phi squared, sorry. The fourth, so rho 1 involves phi to 0, right? Row 2, no, it's not equal. It's proportional to. Row 2 is proportional to 5. Row 3 is proportional to 5 squared, and so on. Since 5 is less than 0, is less than 1 in absolute value, this will be an exponential decay. Could be alternating signs depending on the sign of the coefficient of 5. Okay. So in fact, the autocorrelation function can be written using the autoregressive equation y minus phi b times rho k, for k equals 2 to 3, subject to an initial condition for row 1. So once I have row 1, I can compute row 2, row 3, row 4 based on this equation, because row k is going to be equal to row 5, row k minus 1. So once I compute row 1, once I have row 1, then row 2 will be equal to 5, row 1, row 3 will be 5 squared, row 2, so I have 5 row 1, 5 squared, row 5 row 2, sorry. Oops, I lost my pencil here. 5 squared, and that will be 5 times row 2. Okay. So the autocorrelations will follow the behavior of the autoregressive polynomial. Okay. And that's an important result for NARMA 1.1, because if I look at we'll start looking very soon at model identification. If I look at the autocorrelation function of a process, and I observe, for example, here for the ARMA 1.1, starting at k equal to 2. Remember, the autoregressive order is 1. The moving average order is 1. When k is equal to 2 and on, the autocorrelation function will have the same behavior as the autocorrelation function for the original series. Okay, because the behavior, apart from this initial condition, will be determined by the autoregressive equation for rho sub k. And we'll see that this will extend to other models. Okay. So in an ARMA 1.1, once we compute the first autocorrelation, the rest are given by the autoregressive equation for the model. Okay, and are determined by, in this ARMA 1.1 case, for phi, which is the only coefficient, only parameter in the autoregressive polynomial. So the parameter theta, the phi, sorry, determines whether the series converges to 0 with alternating signs or not alternating signs. So the parameter phi will determine how it will decrease exponentially, but it may alternate in signs if phi is negative, for example. Okay, and the parameter theta, this is another important thing. In an ARMA 1.1, theta only has a role in computing the first autocorrelation. Outside, once we have the first autocorrelation, theta doesn't play a role. The coefficient, the moving average coefficient, doesn't play any role in the autocorrelations computations. See, these are some examples of ARMA 1.1s with different parameter values. This is 5.9 theta 0.5, 5.9 theta 0.5, minus 0.9 theta minus 0.5, and this is 0.9 and minus 0.5. Okay, so these are different series with simulated from that with those parameters, and these are the theoretical ACFs. Okay. These are the theoretical ACFs. As you can see here, the phi is negative. So we have alternating signs in the autocorrelation function, but the decay is exponential. We have exponential decay with alternating signs. In this case, phi is negative, right? In this case, I'm sorry, this is, I have to put it inside the, in this case, phi is less than 1, less than 0. In this case, phi is greater than 0. And we have exponential decay, but there is no alternation in signs. And in this case here, we have phi is negative also, and we have alternating signs, but the exponential decay. Here we do not have alternating signs. I'm sorry, we have a sine wave, like the type of behavior we saw when we studied the autoregressive models. As you can see here, we can have a sine wave pattern, right? And so, okay. But what determines the behavior is going to be the parameter phi. Okay. Theta only plays a role in the computation of the first. So theta is involved only when you compute the first, or no, I'm sorry, that's not it, because that's like equal to 0. Phi, theta has a role only on the computation of the first autocorrelation. This one, this one, this one, and this one. Okay. Those are the only autocorrelations where theta is playing a role in the computation, in its computation. Okay. Apart from this point, it all depends on phi, the behavior. Okay. Now let's generalize this thing to an ARMA PQ. In an ARMA PQ, we have P, the autoregressive polynomial is of order P, the moving average polynomial is of order Q. Now, for the process to be stationary, we require that the roots of phi of x lie outside the unit circle. And for the process to be invertible, we require the roots of theta of x equals 0, lying outside the unit circle. Now it can be shown that the autocorrelations for an ARMA PQ, we will not go through the detail, but it's an extension essentially of the ARMA 1-1 result. We could do it for the ARMA 1-2 or ARMA 2-1 and look at the behaviors and generalize that. But it can be shown that for an ARMA PQ process, rho sub k will be equal to phi 1 rho k minus 1 plus phi 2 rho k minus 2 and so on up to phi p rho k minus p for k greater than q. So we saw it in the first in the ARMA 1-1 when k was greater than 1, when q was equal to 1, right? When k was greater than 1, the autocorrelation function was dictated by the autoregressive polynomial, which is what we have here. That is, in other words, what we have is that 1 minus phi 1 b minus phi 2 b squared minus phi 3 bq minus up to phi p b to the p rho k is equal to 0. That's the behavior for the autocorrelation function for k greater than q, which is what we saw for the ARMA 1-1. We saw that for an ARMA 1-1, we saw that for an ARMA 1-1, we saw that 1 minus phi rho, 1 minus phi b rho k equal to 0 for k greater than or equal to 2. Okay? Or greater than 1. Okay, that'll be the same as saying, to put it in the same terms, that'll be the same as saying that greater than 1. Okay, which is what this expression says here. Now, for k greater than q, for all lags that are less than q, the order of the moving average model, the autocorrelations will involve the parameters theta k minus 1 plus 1 up to theta q. And since with, and again, this can be shown for the general case. If q is less than p, then if q is less than p, the autocorrelation function is completely determined by the difference equation given by the autoregressive model, the autoregressive part of the model. Okay, so if q is, that is, if the moving average order is less than the autoregressive order, then the autocorrelation function will be determined completely by this difference equation for k greater than p. Here we're assuming that p is greater than q. Okay, but it will be subject to initial conditions that are determined by the first p values of the autocorrelations, where in these p values, theta does play a role. Okay, the thetas play a role. That's if q is less than p. If p is less than or equal to q, that is, if the opposite of this, if p is less than or equal to q, then there will be q autocorrelations that will not follow the original, the ACF behavior of the autoregressive part of the model, but will behave and will behave according to this thing for rows of q plus 1, rows of q plus 2, and so on. Okay. So the behavior of the autocorrelation function, whether q less than p or greater than p, greater than or equal to p, will be determined by, in one case, it will only be determined by the parameters theta k up to theta q, okay? And in the other case, where p less than or equal to q, we have the equation will apply the autocorrelations rho q plus 1, q plus 2, and so on will behave according to the same model. The order, this is exactly the same autoregressive model that determines the behavior of the correlations here. Okay, but here it will only be true for q minus 1, lags q minus 1, q plus 1, q plus 2, q plus 3, and so on. Okay. Now, it is not trivial to remember all these things. And in particular, when we start looking at the data and looking at the autocorrelation function, then the partial autocorrelation functions, what will help us determine the orders of the polynomials p and q will be practice. Okay. Because remember, we're dealing with observations that from a random process, which is not, we do not know the true model. So we have to make guesses about what the right orders for the autoregressive part and the moving average part are. We'll be seeing when we do the examples that it's not immediate, and at the first time we had the right model, that's not in general, it's not possible. We have to try different models, and we'll go over that when we talk about the model construction. We'll go about the process to identify which is the model that best represents a time series that we're dealing with. Okay. Now, in general, most of the series that we deal in practice, let me put this thing sounding a lot. Most of the series that we deal in practice are either not stationary, or do not have constant variance, or are influenced by semi-deterministic behaviors such as seasonality. Okay, most of the series in practice are not perfect series to analyze. So we have to make them as perfect as possible to be analyzed and to be able to train a model. We already mentioned that when we have an adaptive polynomial trend in our series, we can correct that taking differences. Okay, we'll dig in, we'll go deeper into that thing when we talk about ARIMA models. But we still have to deal with the problem of non-constant variance. We find a lot of series in practice that do not have constant variance. Where in the cases where we do not have constant variance, before we take differences to remove the polynomial trend, the adaptive polynomial trend, before taking differences, we need to stabilize the variance. And the family of functions, the family of transformations that we'll use are the Box-Cox transformations, which are given by this expression here. The transformed series ZT transformed is going to be ZT to the lambda for lambda different from 0, and log or natural log of ZT if lambda is equal to 0. How do we determine lambda? We'll talk about this thing more when we talk about the model construction. But the idea is to choose lambda so that the variance for the series is roughly constant. Okay. This transformation, Box-Cox transformation, is used in regression. It's used also in time series. And it's used in general in other procedures that require normality. That require normality. In the case of time series, what we want is the lambda that makes the series constant. We're not aiming at achieving normality, but we're aiming at achieving a constant variance. So the criteria to choose lambda for regression problems and for other problems where we look for normality is different. The criteria will be that we use for time series is to make sure that the variance doesn't change with time. Okay, so it's different criteria. If you use the lambda, a Box-Cox procedure for regression to choose lambda, the lambda you're going to get there is going to be different than the lambda that you obtain in a time series context because the objectives are different. And we'll talk more about this, how we choose lambda here. Okay. Now let me escape here. And the best way to start dealing with these type of models is this script. You already worked with this script before. Is the SD06. It's called Procesos Arma. Procesos Arma. Okay. Please download your script to your computers, and actually I can remove these lines here. I'm not going to use them. Remember that in this procedure I create a function to generate time series that can be models of order ARMA 1, ARMA 10. So this function here, this function will help me create models for ARMA. Could be ARMA 10, which will be an autoregressive order 1, ARMA 20, which is this is AR2, AR1. I can generate MA1, MA2, and I can generate ARMA 11 or ARMA to 2. Of course, the function can be extended to generate data for other models like an ARMA 3.3 or something. This is just limited to a second order autoregressive polynomial and a second order moving average polynomial. Okay, so download that script. We're going to generate several series and look at the theoretical and the actual autocorrelation functions and partial autocorrelation functions, because those two used together will help us identify the orders of the polynomial. So run up to the function, you finish running the function, and that's about all this part here. Just run that.
I'm ready.
Okay.
Ready.
Okay. We already generated some AR processes and some MA processes, I believe last time. So let's just focus now on the ARMA processes. Let's look first at ARMA 1.1 models. Okay. Well, for example, I start with this one. We'll generate 200 observations from an ARMA 1.1 with parameters phi1 equal minus 0.8 and phi2 equal minus 0.6. Okay, so we'll generate this model, and first let's look at the series. That's a series, and what we had mentioned before is that just looking at the series is very difficult to realize if this is an ARMA model or an AR model or an MA model. Okay, so we'll be focusing on the theoretical and the sample autocorrelation functions. This is an ARMA 1.1. Notice that phi1 is minus 0.8, so it's negative. So the theoretical correlation function, the theoreticals one are autocorrelation and partial autocorrelation functions are in the first line. And these are the bottom line, the bottom two plots correspond to the sample autocorrelation and partial autocorrelation functions. So notice what happens here in the phi is minus 0.8. So that's why we have alternating signs. Okay. Now, what I was telling you, what we just saw now is that the behavior for an ARMA 1.1 after from live 2 and on, the autocorrelation function behaves like the ACF of the original series. Okay, that's the pattern that it follows. Now, this is the theoretical ACF, and this is the partial autocorrelation function, theoretical partial autocorrelation function. You can see the behavior of the ACF here, how it's alternating sign because phi is negative. And it's dying very fast. Okay, it's dying very fast. And on the other hand, if you look at the theoretical partial autocorrelation function, we saw that in the case of an pure AR model, the PACF tells me the order of the autoregressive component. In a pure AR, this is not the case here. I can have guidance into what type of order or model do I have. These are the theoretical ones. Okay, so you need to get familiar with different theoretical ACFs and PACFs for different models. So that's why I want you to use this function to generate more models and look at how these theoretical graphs look. What we'll be dealing with, and this is a simulated data, so it's easier to model because it's simulated. But what we'll have to do is working with the sample autocorrelation function, the sample partial autocorrelation function, identify the right model. And as you can see, the behavior here is very clear. Alternating sign decay exponentially. It's not that clear here. But what we can see from here, when you see something like this in your sample data, where you have probably two lags. Here it looks like the second lag is also significant, okay? And also here in the ACF, the second lag is also significant. In a case like this, the natural thing to do will be start with a simple model because it looks, this ACF is dying very fast. And this one is also dying very fast, indicating that's probably very low order on the autoregressive part. And this is indicating a very low order polynomial in the moving average part, if there is at all a moving average part. So in this case, we will start trying to model an ARMA 1-1. Feed the parameters and see if the model is appropriate. Okay. Now let's look at the next series. This is another ARMA 1-1, but here phi 1 is 0.5 and phi 2 is 0. That's because it's a second order autoregressive polynomial, and theta is equal to 0.8 in this case. Now, as you can see, there's no alternating sign, but it's a very fast decay. It's very fast decay. And here, the alternating sign occurs here in the PACF. The PACF indicates if there is autoregressive components or not. The fact that I have a PACF that has a large value here. Let me see here. This is a PACF, and that's like 5, 4, 3, 2, 1. Yeah, that's correct. That's like 1. And I have some behavior that alternates in sign here. And that's a theoretical one. Here's I have the exponential decay, and here I have this behavior of switching signs, right? Now, that's the theoretical VACF. What we will see, we will not see these charts, but we have to be able to, based on the sample ACF and the sample PACF, try to figure out in terms of the theoretical ACFs and PACFs that we know, which type of model could that ACF and PACF correspond to. Okay. Now here this makes it, if we knew that this was a pure AR model, if we knew that that was a pure AR model, we would fit an AR3 model based on this data, okay? Because the first 3 autocorrelations are different from 0. So if we knew if it's a pure AR model, the fact that I have certain behavior here, and I do have some behavior that resembles the exponential decay here, makes me think of 2 possibilities. I either fit an AR3 or I fit an ARMA 1-1. Okay, because of the rate of decay of this, the rate of decay here indicates that very low order of an AR polynomial if there is one. So the parameters tend to compensate each other. Okay, so if you fit an AR3 model, you may get a reasonable model, but you also need to try the ARMA 1-1 and look at the model that best represents your series, and then select among those that give you a good representation of the series, select the one that's more parsimonious. Okay, so if we fitted these 2 models, probably we would get reasonable results in both when we fitted the models, but we would choose the ARMA 1-1 because it's more parsimonious. But again, we will rely on the diagnostics to be able to determine if we are identifying a correct model or not. We will have to do that. And it's just a matter of practice. It's not something that you do and you identify the perfect model the first time. Okay. Just look at what happens now with this other series here. That's another series. And here it looks like there's this autocorrelation seems to be strong, okay? The partial autocorrelation dies out. But if you look at the sample data, it looks like I may have two AR terms because I have two significant autocorrelations. So what would happen in practice maybe, if you have a series that showed this type of behavior, this PACF and this ACF, you would probably fit an ARMA 1-1 or an AR 2 model, okay? And compare them. Now, if neither of those two models gives you a good fit, then you need to try something different, okay? So the identification and fitting process is an iterative process. It's not, you do it once and you're done. You have to try different models, okay? Because it's not that clear just from the charts. You can see that it may not be a pure AR model because of the behavior here. May not be a pure AR, but there's a doubt, so you could check an AR2 model or check an ARMA 1-1 model, okay? There's no problem. Once you get the results of the fit, you look at the diagnostics and look at the value of the coefficients to see if they're significant or not. We'll look into that when we talk about estimation. And then this other one here, it's again an ARMA 1-1, and here it looks like the AR part is of order 1, but there may be an MA component also because of the way this thing is behaving, or the autocorrelation function is behaving. These are the theoretical ones, okay? When generally, you will see in practice that the orders of P and Q are not going to be too large. If you fit a model that has P equals to 5 and Q equals to 4, you're probably doing something wrong. You're probably, you need to transform your data, or you need to look at different alternative models. Maybe you're missing a seasonality behavior or something, okay? That's an ARMA 2-2. Again, just looking at these graphs makes it difficult to figure out if it's an ARMA 1-1 or an ARMA 2-2. What will give you the tools to be able to determine which is the right model is going to be practice. Looking at several series, analyzing them, looking at the ACF and the PACF. When you see behaviors like this, where you have this thing is dying, it looks like the most you would get in the autoregressive order will be an order 3, the most, okay? But that's already too close to the band, to this band here. But the fact that you have alternating signs here, it's a clear indication that you have an autoregressive component. So in this case, it's very clear that you will have an ARMA model. It's not that clear that it will be at 1-1 or 2-2 or something like that, okay? So in this case, it's an ARMA 2-2, but you can fit, you will start fitting either an ARMA will start, there's two routes. One, you start with a higher order model and start modifying it until you get a simpler model that represents your series well. So what I would advise you is to take this script and generate